All right, so this is the pre-lab video for experiment number 17, where we're going to look at some emission spectra. All right, so this is going to be the pre-lab video. And so what we're going to do is we're going to talk a little bit about the theory behind how an emission spectra works. We'll talk about what we're trying to accomplish with each of the two parts. We'll walk through a little bit of the sample calculations, and then we'll move forward from there. All right? So the idea behind it is that when we are exciting an atom, let's say that this is our nucleus down here, and these are our different energy levels. Our first level is n equals 1. Our second one is n equals 2. The third one is n equals 3, and that continues on up. Now, when we excite an element, we're basically changing electrons. We're taking them from one energy level, and we're moving them up into another. So this one could be moving up into number 3. There we go. Or we could be taking an electron and we could be moving it from n equals 2 to n equals 3. Right? And so this is all happening when they are absorbing. So these are absorbing photons. So we're doing this when we're exciting an element, electron. Now, from there, what we're going to do is that for an emission spectra, we're going to wait. We're going to wait for those electrons. After they're excited, they can start to release energy and fall back down to a different ground state below them. So they might fall down from n equals 3 to n equals 2. They could fall down from n equals 3 to n equals 1. And with each of these processes, when we have that change in energy, they're going to emit a photon. Now that photon will have a specific energy that's tied to that distance or that gap in energies between each of those energy levels. So n equals 3 to n equals 2 has a different photon than that of n equals 3 to n equals 1. So when we do that for an element, we can see different bands of light that might get released by these emission processes. And that's going to be our spectra. So each element has a slightly different spectra because they have different energies for their energy levels. So by looking at those spectra, we can kind of figure out what process is going on for them. And so this is how we can identify elements. It's to look for a spectra that might be only emitted or absorbed for a very specific element. And if we see any interaction with the photons at that specific wavelength, we know that that element is going to be present. For an example, we're going to start off with that of mercury. Now, mercury has a couple of different distinct lines that we can see. It has one that's in the violet region, over at 400 nanometers. It has one that's in the bluer region, around 435 nanometers. It has one in the green region, right around 546 nanometers. And it might even have a last one in the yellow, which is about 579 nanometers, right? So it's got 4 different lines that we can see, and each of those lines corresponds with a transition. So this is an electron transition. And so we have that difference in their processes. Now, for part 1, we're going to calibrate our spectral photometer. Now, what that means is that we're going to have a light of mercury, and it's going to be releasing this light out. Now, normally we would see all of that at once. And so what we need to do is we need to use a photometer, or we call it a spectroscope. And what that spectroscope is going to do is it's going to allow just a little bit of light in. And as that light comes in, it's going to get diffracted into different colors. So we can separate the yellow beam from the green beam, from the blue beam, from our purple beam. So we can see those different values. Right? And that's what we would be looking at. Now, sometimes they do that with a mirror. They can also do that through a grating. It depends on your different types of spectroscope. So what we're going to do is we're going to measure those distances that we would see over here in order to get an idea about what values we're seeing. So we're going to use a standard from our mercury lamp. And we're going to record the distance in centimeters. And then we're going to eventually use those standards to create a calibration graph. Now, that's what's going on in part 1. So in part 1, we're going to take that data, we're going to graph it, we're going to find that trend line, and that's going to allow us to help predict things, right? And we'll go over how you can do that inside of your lab data part. Now, for part 2, we're looking at a hydrogen spectra. And we're going to determine its wavelength. So what we're going to do is we're going to record the centimeters of the lines. We're going to use our calibration curve, or really our trend line. To predict the value it should be in nanometers. So let's say, for an example, we had measured something that was 3.0 centimeters, and we had a trend line from our graph before as y, which is basically our wavelength, as being 101.3 x plus 2.7, right? And though this is our trend line, And so this X is that in centimeters. And so what we can do is we can take that 3.0, and so we plug that in for X. So we can have 101.3 times 3.0 plus 2.7, and we can find our wavelength. And in this case, it's going to be nanometers, since that's what we had inputted in our calibration graph. So when we do that, we get 101.3 times 3 plus 2.7. And we get a wavelength of 306.6 nanometers. And so that's how we can calculate our wavelength. Now, this isn't the trend line you should use. You should make sure that you use your own trend line from the graph. And then we can try to find our percent error. So your percent error is take your actual value minus your theoretical, divide by your theoretical, times 100%. And so if you have a positive one, that means that your actual value was higher. If you have a negative one, it means it was less than. And that's how you can get your percent error. Now, as you continue in part 2, they want to take that energy or that wavelength, and they want us to convert that over into kilojoules per mole for that energy of that photon. So we're trying to take a wavelength and move it to an energy of a photon, and then take that energy of that photon in joules and convert it over to kilojoules per mole. Now, the energy of a photon is equal to Planck's constant times its frequency. And we know that the speed of light times the wavelength times the frequency, the speed of light is equal to the wavelength times the frequency. So we can combine those to get our energy of our photon is Planck's constant times our speed of light divided by our wavelength in meters. So we know that we have a wavelength of 306.6 nanometers. And I can find its energy by plugging that in. And you multiply it by 10. And you divide it by 10 to the 9 nanometers, 1 meter. I can plug that into my equation. I can use my speed of light, 2.998 times 10 to the 8 meters seconds. And I can use this for my meters. You can see that my units are going to cancel, my meters and my meters, my seconds and my seconds. And so we're going to get this as the energy of a photon, joules. So that becomes 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8. That's an eraser, 6.479 times 10 to the minus 19 joules. Now, they want it in kilojoules per mole. So I want to go ahead and change that. So this is really kilojoules per photon. So to change that over to moles, I need to multiply it by Avogadro's number. Because that's the number of photons per 1 mole. And then to get into kilojoules, I want to use the conversion that there's 1,000 joules in 1 kilojoule. And so if we do all of that, we should get something like 390.17 kilojoules per mole. And that's going to be our photon energy. Now, to get from here into our conversion factor, they want to know what transition this could be. And so for us to find that transition, we kind of have to look and see what our values of N it could be. Now, when we compare that back to the figure that they're talking about in the very beginning, we can kind of see the energy values that they're giving us, right? So they have several different N's. We have all the way at the top, N equals infinity. Then very close to that, we have N equals 5, N equals 4, N equals 3, N equals 2, and at the bottom we have N equals 1. And so mathematically, you can solve for them, or what you can do is you can look at their transitions and you can try to see what that transition would be between them. So right now, each of these values has a different energy. This one is said to be negative 1310, negative 328, negative 146, negative 81.9, negative 52.4, and 0, and all of these are in kilojoules per mole. So if I was going to transition from 0 or from infinity to N equals 5, my transition should be a change of the emission of a photon that has 52.4 kilojoules per mole. If I went, actually here, we're lining up these colors a little bit. If I went from N equals 5 to N equals 2, then I would have a transition of our energies. So negative 328 minus, negative, sorry, 52.4 minus negative 328. And that would give me my energy of 275.6 kilojoules per mole. And that's how much I would have to be releasing in order to make that happen. N equals 4 to N equals 2. Has a different transition. It's negative 81.9 minus a negative 328. And so it's giving me a change of 246.1. And so you want to line up this difference with the one that you have for your calculation to see what best transition it corresponds to. Now, unfortunately for ours isn't really going to correspond to one of these because I made up our centimeter sign. And so you're going to have to look through yours to see which of those values best lines up. And that's how you find your initial state as well as your final state. Once you have all of that, then you guys can plug into your equation to look for your RH. And you'll find that in terms of kilojoules per mole. Because what you're going to be able to do is you can solve for this equation. You know what your delta E should have been, or what your delta E is. And you're going to know that that's going to be RH of 1 over your initial squared minus 1 over your final squared. Or in this case, they describe it as n2 squared minus 1 over n1 squared. So depending on which value you're considering n2 versus n1, then that's how you can double check those. Now, when you want to do your comparison, your literature value is 1317.0 kilojoules per mole. And there you go. That should be all the calculations you need in order to get through this lab. Go to your next one to figure out how you get your data.